Now, before I run the analysis, I'm going to go look in this MFCC analysis patcher. And we'll eventually trigger this with a bang. We'll do it from right inside here. And I want to look at what's going on because this patcher, you'll notice, does not have buff MFCC here. Buff MFCC here does not have a features attribute. So the question would be, well, where is this buffer analysis writing the MFCC values, right? They seem to be happening somewhere, but there's no visible buffer about where that is taking place. Well, the way these objects are designed is that when you create one of these FluCoMa analysis objects, it actually creates internally a buffer that is a private buffer that it doesn't really show you, but it makes it, it holds on to this private buffer inside of the object. That's sort of a metaphor. It's not really inside the object, but it's right. It holds on to its own private buffer. And if we notice what this actually tells us, if we run the operation, is it tells us buffer, and then it has a big old string of characters here. This is actually an identifier that Max can use to find that secret hidden buffer. And when we pass this message, buffer identifier, to buffstats actually automatically will read this as set this buffer to be the source, and then do your thing, run your statistical analysis. So this actually says source MFCC. We could actually delete this because we're telling the source is this. So then if we hit it again, we're actually passing this buffer to buffstats, and it's doing a statistical analysis on this buffer. That is the private buffer of fluid.buff MFCC. And then if we look at what buffstats does, is it'll do the same thing. It has a private buffer that it will write the statistics into. You'll notice we don't have a buffer here that we're specifying where it should write its output, its statistical summary, but it in fact does, and it is called this. So then we pass this message to bufflatten, and this buffer, or this object, bufflatten, will set this buffer as its source. Again, we have a thing in here, but this doesn't need to be here. In fact, it's not even being used because this will overwrite whatever we had in here. And then output it's into here. We do have a destination, a buffer called flat. And so this is the automatic buffer management system that these objects that use buffers and output buffers will actually hold on to a secret private buffer and then pass it along the chain if you connect the objects in a particular way so that they know what to do with this message they receive, buffer something. In fact, bufflatten also, if we delete this buffer called flat, this will throw an error because the buffer flat doesn't exist anymore. So the data point won't know what to do, but we can see that, or the data set won't know what to do with this message, but we can see that bufflatten also has a buffer. And so this can be nice because now we don't have to make quite as many buffers. Data is automatically being passed around. This is a single private buffer that buff MFCC has. And each time buff MFCC does its processing, it will overwrite the contents of this buffer, just like buff MFCC would overwrite the contents of a buffer if we did specify a features buffer. If we had a buffer in here like at source MFCC analysis, right? This buff stats by default, if we send it a bang, it's actually going to look at this source MFCC analysis. But as soon as we send it this message buffer and then the identifier, this buff stats will overwrite its source attribute here, and it will no longer look at MFCC analysis, even if we send it a bang later. As soon as we send it this, it overwrites this attribute and will only look at this buffer from then on out. There's also other objects in FluCoMa that do this. We can see here that the fluid buff HPSS has a source. It is the drum loop. And I'm specifying a harmonic and percussive buffer output about where the harmonic output and the percussive output should be written into. But if I were to delete these, just specify the source, buff HPSS also has some hidden buffers where it will output the harmonic and percussive components it discovers. This will output the name of the harmonic buffer. This will output the name of the percussive buffer. And you can see that the fluid waveform object is designed so that if it receives the message buffer something, it will display that buffer. So that's pretty nice. And also, this is going to be a bit of a weird hack. I think it'll be fine. Fluid.buff2list can also receive a message buffer blah, 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 or I should say buffer and an identifier of a buffer, and it will output for me the contents of that list without even having to specify a source. And so you can start to chain together these FluCoMa objects in such a way that they will talk to each other and know what each other wants, but you don't have to make quite so many buffers, and you don't have to keep track of buffer names all the time, which can be a common source of error, because if you just have a typo in a buffer name, right, you're going to get a bug and you're not going to necessarily know how to find it. And so this automatically takes care of that for you, and you don't have to worry about it as much. There's one more thing I'll show you. So we have our drum loop in here. We'll do the slicing. We'll do the analysis. And now we have our data set called slices, which we can print and see here. Here's our drum slices with our spectral centroids and loudness values. And now if I were to take this fluid normalized object, and I want to do a fit transform on my slices data set, but rather than writing it into a data set called normed, I can actually take off this argument. And this will still run for me, no error. And what it's doing is this fluid normalized object is holding on to a secret hidden data set that it will write the values into and then report out for me when it is complete. It's saying fit transform. I've successfully done that task you asked. And since you didn't specify an output data set, I will use my secret internal data set and tell you what that identifier is. And so there's a data set with this as its name that is hidden from view that we can still use. And what's nice about this is the fit transform message is the same message as UMAP. So now if I say UMAP, fluid, yeah, there you go, fluid UMAP. This message going into UMAP will be fit transform and an input data set. So UMAP will know what to do. It'll say, okay, I'm going to fit transform. I'm going to, use this as my input, and then it'll output for me a data set that is its secret hidden data set. And so you can see now how this also can be a convenient way of avoiding worrying about typos and automatically connect these objects together in a way that they already know what it is that you want to do with them. When I do this analysis and I'm going to add a point to a data set, I might want to know the name of that buffer so I can put it in this message. Now, there are ways that you could actually, route off the buffer message here and then store that in like a register of some kind, and then increment your counter and then retrieve that with the identifier and then pass them both to data set. You can sort of build a system where you're keeping track of the hidden buffer identifier and then eventually using it here as an argument or as a $sign argument. That tends to be a little bit more complicated than just doing it this way. So, that is to taste. But this is a common place where you just want to have a buffer with a name. Another one with the data set is that if I want to dump the data set, I actually need to be able to see the data set to send that message to. And so I need to have a data set with a name. It actually doesn't have to have a name, I guess, but I have to have a data set physically on my max patcher here to send the dump message to get out the dictionary to send to the plotter. So that's an example where you would need to have a physical data set or a present visible data set.